Here we go with static electricity. Thanks to Joe Cossett for a lot of the PowerPoint work. Let's start. So what happens when you rub the balloon on the sweater? We saw this in our lab activity where we rub the balloon on the sweater. And let's just watch it. And we see that the electrons are coming off of the sweater, giving this a net negative charge to the balloon. If we let go of the balloon near the sweater, it's going to be attracted to because opposites attract. Whoop. If we bring it towards the wall, then the electrons that currently reside in the wall are going to run away because likes repel. So that's going to leave a net charge of positive on the wall. So we can get the balloon to stick to the wall. Or we can get a pencil to stick to the wall. Or we can get whatever to stick to the wall. Anything that's holding a net negative charge will stick to that wall. The protons and neutrons are buried deep in the nucleus and cannot easily be touched. Electrons orbiting the nucleus are easily gained or lost, especially those valence electrons that maybe you learned a lot about in chemistry. John Travoltage is going to be picking up some charge as we rub his foot on the carpet, and that extra charge is just going to hang out on the outside of his body. It's going to look for some place to go, the nearest conductor, and there we go. Once we've built up enough charge, then it can make a bigger leap. If we're closer, then the charge happens, or the discharge happens a lot faster. So that is the first way that an object can become charged, through friction, through the moving of those charges. Another way can be through contact. If we take a net negative charged rod and place it next to a neutral sphere, I know it's net negative because there's only 2 protons. The black ones are electrons. This has 3 and 3. Once we touch, then we start to see, get out of the way, then we start to see the electrons moving onto the neutral object. And the final way would be through induction. And induction happens without contact at all. So you can see negative, we have 2, 4, 6, 2, 4, 6. We have a neutral cloud, but the negative charges are hanging out lower in the cloud. So that means in the ground, the electrons are going to stay away from the negative. Right? So the ground becomes negatively charged, and the cloud is negatively charged. Here's induction. Electrons move within the object, making the closest side oppositely charged. Negatively charged rod, a neutral sphere becomes positive on one side. This is charging through induction. Now we have intra-cloud flashes, lightning, right? The discharge of built-up static electricity within the atmosphere. So within the cloud, you have charges. Negative cloud to ground flashes. The negative charges to the positive ground. Positive ground to cloud to ground. Holy cow, Mr. Scapetta, start reading. And then we have intra-cloud flashes. So the lightning happens because of a rapid heating of the area around the charges. So as the charges get discharged, and they're in such a large quantity, the charges become discharged, they ionize the air, allowing for this pathway for the lightning to come through. So now that you know a little bit about static electricity, use it responsibly, late at night and without permission. Review of charges. Opposites attract. Likes repel. Which charged pair has a larger electrostatic force acting. This one. Smaller distance means you are going to experience a greater electrostatic force. Meanwhile, which charge pair has a larger electrostatic force acting? We have two equal charges, distance r, and then we have one charge that has a greater total charge, same distance, r. Greater charge is the greater the force. All right, so we actually have a formula where we can calculate this. This is called Coulomb's law. The force of attraction or repulsion between 2-point charges is directly proportional to the product of the two charges and inversely proportional to the square of the distances between them. Represented like this, where F is the electrostatic force measured in newtons. Object 1 is going to be charge 1, represented with a Q, and the unit of measurement for charges is going to be the coulomb. Coulomb. Same for charge 2, measured in coulombs, and the separation distance, R, measured in meters. Now, hopefully you saw this and you said, wait, that looks familiar. That kind of looks like Newton's universal law of gravitation. And you'd be absolutely correct. We're going to go into that a little bit more. But first, how are these charges measured? So charges are quantified, which means they only appear in multiples of the elementary charge. And the way the elementary charge was determined was through this simple seeming, but really genius way. This is called Millikan's oil drop experiment. And in this experiment, we have this atomizer that takes this oil, and when you press down on the atomizer, think of those old perfume bottles, press down on the atomizer, the oil is sent through in about the size of an atom. So an atomizer, the oil droplets are in this upper chamber, and it passes through a positively charged metal plate. So they're going to pick up a charge. And then there's a negative plate down here. So they want to be attracted to the bottom, right? Plus gravity. So they're going to be falling. Well, there is also an ionizing X-ray that comes through. So by turning on the ionizing X-ray, it's going to ionize those little oil droplets and allow for the electricity, the electric force, to take over rather than gravity. So this guy Millikan was able to change the amount of these charge plates until just enough to where he could suspend the charges. And from that, he was able to determine the charge of an electron or a proton, the elementary charge, which is 1.6 times 10 to the negative 19. This is his actual device. On your data table, you'll notice the elementary charge is given to you as E, 1.6 times 10 to the negative 19 coulombs.